Good morning, friends, or afternoon, or evening, or whatever it happens to be while you are listening to this. So today we're going to start with doing a little bit of a recap of the types of stars from your HR diagram, Hertzsprung-Russell diagram, and then look at a little more of the detail around the life cycle. So the diagram we were looking at in the book was placing stars on a graph with the temperature on the x-axis and their absolute magnitudes on the y-axis. One of the things that was weird about this graph is that the temperature scale actually ran backwards. The cooler stars were on the right, moving towards hotter stars towards the left, which is usually the reverse of how we set up our x-axis. And then the absolute magnitude was increasing as we went up the y-axis, which kind of makes sense. That's what we're used to. Most of the stars fall along a nice straight-ish line down the center called the main sequence. And then there were a few other groups of stars that you were looking at that were scattered around that have to do with the parts of a star's life cycle after it has finished its time on the main sequence, which was the time where it is burning hydrogen into helium in the core. So the white dwarfs here are a section that belongs down here. They're below the main sequence, which means they have a much higher temperature, but they're a lot dimmer. They're a lot smaller. So there's one here shown in the photograph where it is scaled to the size of the Earth. You'll notice that it's about the mass of the sun, but it's the size of the Earth. That's a lot denser. So these are dense stars. They're very hot. And they're very small compared to similar stars on the main sequence. The red giants, and one of the questions we did asked you to compare red stars in a couple of different locations on the HR diagram. These ones belonged, here's my main sequence, the red giants were up here, and then super red giants are up here. So at the same temperature as their main sequence counterpart, they're much brighter. They're very large, but very cool by comparison to stars that have the same brightness. So a star on the main sequence with this brightness would be all the way over here. Remember, this side is hot and this side is cool, in stellar standards anyway. But they're much bigger, which means they have a very low density. The surrounding gases are only loosely held on by gravity. So there's three shown here. Our sun is not a red giant, it's just in there for scale. Our sun, when you saw it on the graph, is about right here. The smallest red giant is cooler than our sun and a lot bigger, and then the largest of the Kepler red giants, which is just a group of stars, is much larger than our sun, despite the fact that it is cooler. So one of the other questions we looked at was, what are some of the conditions needed for life, and what are some stars that might be ones that could support planets that have life on them? There's a few things we need. We need the right temperature. The energy output needs to be in a good range where we have liquid water present. We don't know of any forms of life right now that don't rely on liquid water. And there needs to be hydrocarbons. Again, this is our current understanding, but we need those class of compounds that involve bonding hydrogen and carbon together. So we need enough gravity to hold in an atmosphere. We need enough gravity to hold in water, which means you need a large enough mass. In our solar system, the Moon and Mercury are too small for an atmosphere, so they can't hold it in. Venus does have an atmosphere. It actually has a very toxic atmosphere. So you need something, you need that Goldilocks zone. And that's actually what this picture is about, is this Goldilocks zone of habitability, meaning the range of distances from the star where it's possible to have liquid water. So the blue star at the top there is very hot, so its Goldilocks zone is quite further out, quite a ways out compared to the Goldilocks zones of the other two stars. If I put them side by side, the blue supergiant is super hot and super big, and we talked last day about how stars with a high mass are going to use up their hydrogen very quickly, so it's a rather short lifespan. It doesn't give enough time for life to evolve. The yellow dwarf, this is like us. Moderate size, moderate temperature, which gives them a fairly long lifespan. our sun is probably going to last about 10 billion years, we estimate, given the lifespan that we've measured of similar stars to us. Red giants are small, they're fairly cool, they have a very long life, so they have lots of time to develop planetary systems and then to have some of those planetary systems possibly develop life. So it gives us an idea of what kind of stars to start looking at if we're trying to think about where we might find planets that are habitable and planets that are similar to Earth. One thing that it's important to remember about the HR diagram is that this was done in terms of the absolute magnitudes because we can't rely on our perception of brightness when we're trying to classify them. Another version of this exercise has you plot a bunch of bright stars and then a bunch of nearby stars on the HR diagram separately. So you're given two lists. And what we end up with is a section down here that's all of the nearby stars if we take their properties. And then the bright ones end up with some that are around here, but then lots of scattered dots. Because it's important to remember that what we perceive as brightness does not take into account how far away the star is from us. So the bright stars are quite scattered on the diagram. They have a variety of properties and they're not all that similar to each other. This is just because when we talk about brightness, we're picking the ones that look bright to us, regardless of distance. Whereas stars that are nearby to us, mainly along the main sequence towards the bottom right, generally have properties similar to each other, because if they're close to us, we are in the same local neighborhood in galactic terms, and probably formed from the same kind of materials, and maybe even around the same time frame. So we have a lot more in common. We tend to associate stars that are close to each other when we look at the sky as being neighbors, but we don't have that third dimension of how far away one is from the other. We just see them close to each other.